Assalamualaikum warahmatullahi wabarakatuh. So this is the final part of topic 7, transmission line model. And example 7.4 is related to medium line model. And we try to analyze and how to solve this question. So the data given, so start with the rating voltage or the supply voltage of 345 kV, three-phase transmission line, 130 kilometer long. So the resistance per phase is 0.036 ohm per kilometer, and the inductance per phase is 0.8 millihenry per kilometer. So this is the data we can gain. So the length of the line is 130 kilometer long, and this is fall under category of medium, of course, because the limit is up to 250 kilometer. So what about the R? So is given by 0.036 ohms per kilometer. So the per phase resistance value. So the inductance per phase 0.8 millihenry per kilometer. So the shunt capacitance. So the C value is 0.0112 microfarad per kilometer. So the receiving end load is 270 MVA, megavolt ampere, and as well as the power factor, the lagging power factor of 0.8, and this is the line to line full load voltage, which is 3 to 5 kV. So now we are asked to utilize the medium line model, okay, the nominal phi model to be exact, to find the voltage and power at descending end and the voltage regulation. So we need to obtain the VR value as well as the Vs descending, V as well as the ascending P. Okay. Solution, this is the equivalent circuit of a nominal phase network or model. So we have IS, so we have the series impedance, so we have IL, the receiving end current, and then this is Vs as well as VR, the receiving voltage, and also the shunt capacitance of Y over 2. So both sides of the shunt capacitance. And this is the load information. We have 270 S power, apparent power, MVA. So this is the line to line full load voltage and the power factor of 0.8 lagging. So the series impedance, so we assume F equal to 60 Hertz, so Z equal to 0.036. This is the R value. Okay, so this is J25 F frequency, and then this is the value gain for the XL. So the inductance value 0.8 millihenry multiplied by 130. So this is the distance or length of the transmission line. And then the final value of Z. So now it turns to calculate the value of conductance Y. So gains, so this is 0. Remember G is 0. Okay, the admittance of the conductance G is equal to 0. Okay, most. And then we have J25 F frequency 50 Hertz, as well as the capacitor value of 0.0112 microfarad. So again, this is the distance 130, and Y in this example giving us J 0.005, sorry, 0.0054899 Siemens. Okay, so now we have done with the series impedance as well as the shunt conductance or the shunt capacitance. So A equal to D, so this is equal to 1 plus ZY over 2. So we have seen the derivation in the previous slide. and then this is 0.98924 plus J 0.0012844. So B equal to Z. So this is 4.68 plus J 39.207. So this is just insert the value of Z as well as the dy. Okay, similarly for B and also C. Okay, so we have y over here, and we have the multiplication between Z and Y. Okay, then this is the final value of C. Okay, so now we have done with parameter A, D, B, and C. Okay, so just leave it there. Later on, we gonna use all this for value. Okay, so the receiving end power, apparent power, three phase, of course. So this is 270, up cos 0.8, the angle. So this is from the equation. Okay, 270 MVA with 0.8 power factor lagging. So note that this is a lagging power factor, and thus so we have the positive sign of angle. All right. So 250 out cos 0.8 giving 270 plus 36.87 degree MVA. So if you convert into rectangular form, so we have the in term of PR plus J QR. Oh, sorry for before that. So you may calculate the per phase receiving end voltage. So you have the 3 to 5 is actually the line to line full load given by question here. Okay, 3 to 5 line to line full load voltage divided by square root 3 to calculate the per phase receiving end voltage. Okay, so giving us 1 at 7.64 degree angle kV. Then here is the IR per phase, or the receiving current per phase equation as conjugate as R conjugate over V 3VR conjugate. So 270, remember the conjugate expression symbol. So make sure now we have the negative value of angle. So over 3 multiplied by 187.64. This is actually in kV. This is, I believe, in meg. So we have 10 to the power of 6 divided by 10 to the power of 3, and then you cancel out. This is actually 10 to the power of 3. So we have only 10 to the power of 3. So here no more 10 to the power of 3 because the operation has been done earlier. And then giving IR per phase 479.64 minus 36.87 ampere. So this is the sending current. Remember from our short line equivalent circuit or short line formula. So since the sending part is still fall under short line category, okay, so we may use this parameter C and D, okay, that relates to VR and IR as well as IS element. Okay, so we have C and D, which has been calculated earlier, as well as the VR and NS and IR single phase. So this is the final value of single per phase sending end current. And again, using the first equation from short transmission line model. So we have A, VR, and N plus B, IR, single phase. So again, pick A and B from this particular example here. Okay, A, B, C, and D into this equation, multiplied by VR and N as well as IR per phase. Then VS per phase giving us 199.19, 4.012 degree, so volt. Okay, this is volt, this is, sorry, ampere, and this is volt. Remember the dimension, the unit. So line to line multiply the answer you just obtained here, okay, multiply by square root 3. So this two giving 345.01 for 4.012 degree volt. So what about the power factor? So this is the equation. We have cos in bracket, so angle of Vs ln, so there's sending voltage per phase minus angle of sending current per phase. Okay, so in this analysis, so we pick 4.012 degree for the Vs ln here. Okay, and also for the sending current per phase 36.79 is over here. Okay, so 4 minus negative 36.75, so they give you the value of power factor finally equal to 0.7570. And then the apparent power, sending apparent power 3 phase. So this is, remember the equations, 3 multiplied by Vs per phase multiplied by Is per phase conjugate. Okay, so just again substitute the value we just calculated just now. So this is Is, so giving Is in term of rectangular form. Again, this is P, S, this is Q, QS. Okay, how about during no load? So this is, okay, this is the key where IR equal to 0. Okay, so VS line to line, I plus ZY over 2, VR LL plus, I believe this is V. Here we can see from the derivation, of here, all right. So when IR equal to 0, so leaving this relationship, so in this example. Okay. So now when IR equal to 0, we have only 1 plus ZY over 2 VR line to line. So this is actually A, okay, the parameter of A. So rearrange, so we have VR line to line equal to Vs over A, the magnitude of A. So Vs line to line, we just calculate this one. So this is we calculate in the beginning of the analysis, and then giving VR line to line 348.676 kV. Okay, so remember this is a V line to line during no load. So we can say that this is the value of VR. Okay, so L to L during no load. Okay. So in order to calculate the voltage regulation, so we just deduct this VR full load. Okay, line to line full load, of course. So this is given by given in the question. Okay, V full load line to line. This is again from question. This is from question, and this is line to line VR no load here. Okay, so no load. Remember no load analysis here. So this is supposed to be no load value of V. Put it here and minus 3 to 5 from question, and result in value of VR equal to 7.3108 degree percent. Okay, so now we continue with the long line model or analysis. Definitions is length of the transmission line must be equal or greater than 250 kilometer. By the way, as we go through the slides or the derivation of this model, so we'll see that it is quite complicated for your level to have a comprehensive understanding of what the or the derivation of the equation, actually. By the way, we will pass or skip some of the detailed derivation just to use or to utilize the final formula or equations, which is benefit us when we come to the question analysis, okay, or question and solution. So by the way, this is actually taken from Categorize circuit of medium line, but somehow we have the delta x here, as well as the delta x, which is multiplied by the series impedance, showing that the length or the distance of the transmission line has been extended, okay, into a long line transmission, which is greater or longer than 250 kilometers. If you see from receiving end, so this is the distance of x, and this has been extended to a longer distance, delta x. Okay, so this is the total L, okay, which is at minimum of 250 kilometers. So between this new nominal phase, nominal phi network, so we have again the delta x, and seen from R, so we have VR, so we have Vx, and this part we have the conductance capacitance turns over here. So this is Y delta x, okay, Y conductance multiplied by delta x to show that this has been extended by delta x, and give effect to the capacitance or the conductance of the transmission line. Okay, here these two, and this is of course the receiving current. So this is the Ix transmission line over here, okay, seen from this X. Okay, so this is a Vx, okay, reflected from here, and this is Vx plus X. So this is from here to here is actually X plus delta x. Okay, so we have the voltage drop over here is Vx plus delta x. Similarly for sending current, so we have Is x plus delta x, okay, which have been seen from receiving part. Okay, this is Is as well as Vs. So now if we apply within this closed loop KVL, okay, and also at this node, let's say node A, we apply KCL. So we may come up with this relationship. Okay, so this is KVL, so this is the KCL at node A. Okay. So we have again this one Vx plus Vx equal to Vx plus Zx. This is the voltage drop. Okay, here, here. So this is the Vx x plus Vx plus Ax. Okay, so we have the voltage drop over here. Okay, as well as here is Y delta x, or the Vx over here. Sorry, this one Vx. Okay, this is KCL happening at this point or this node. Okay, node A. So we have Is x plus x, also this one. So multiply by these two. Okay, multiply, and this one Vx v delta x, oops, over here. Okay, so we have here and this one. So rearrange and we derive to get this Zix and Y Vx. So when we again derive this equation, so you may get d square Vx over dx square, and this is equal to, this is giving the Zdi x over dx. Okay, so dix over delta x is actually this one. Okay. And then replace into here, giving the value of d square Vx over dx square Zy v Vx. Zy v Vx. Okay. So this is when we take gamma square, so equal to Zy, we try to represent. So we derive again. So I will make it short, revise again, and then we try to implement the second order differential equation, this one. Okay. So with constant of A1 and A2. So this is some of the definition of the symbol above. Okay, so let me skip this one. Okay, this is again for the derivation of Ix. So skip these three. Okay, so now this is the final equation we are going to emphasize. So the characteristic impedance Zc equal to square root Z over Y. So finally, after all this derivation, so we may get that the characteristic impedance is actually Zc. So the notation Zc over square root Z over Y. So this is not 2 but Z. Okay. And again, this is when we apply the here the second order differential equation. So you might calculate, or we might figure out the constant value of A1 as well as S2. So when x equals to 0, so all these are the relationship, and all these are the derivation. And so we have the A2 and A1 relationship. Okay, in terms of, again, we have the characteristic impedance Zc as well as VR and IR. So again, derivation or replacement over replacement, in arrangement over arrangement. So we have reached to this stage, and again rearrange. Okay, and substitution over substitution. Okay, so this is the hyperbolic function actually. And yes, we come to this hyperbolic function again of the long language, making this one more, this analysis more easier approach. Okay, so the hyperbolic cos, the sine cos, etc., etc. So waiting or setting x equal to L, BL equal to Vs, etc., etc. And then finally, so this is as what I explained earlier, the final equation or the final relationship which might very useful. Okay, so we have in terms of VR, in terms of IR, and VR as well as IR, and this is the constant, and here cos or hyperbolic cos omega L. Okay, we have 1 over Zc, hyperbolic sines omega L. So I believe this is the parameter represented by A, represented by B, parameter C as well as T. Okay, so A and B always identical. So here, so we can take out the value, or we can take out the parameter and put it here to have a better view. Okay, in terms of A, B, C, D. So this is the determinant metric lines. AD minus BC equal to 1. Okay. So 1 again, 2, 3, 4 parameter that give benefits while solving the question. Or we may see from second method. So we have the nominal phi representation for long line. This is actually a standard derivation from middle line. Okay, so we have seen the Vs in terms of VR, ZIR, but we do have the Z prime and Y prime. Okay, so this is again what I told you, extended by from the medium line. So we have Z, the new Z, which is Z prime and Y prime. Z prime again we have for IS, Y prime, Z prime, Y prime. So plus this is D, which is equal to A, Z prime, Y prime. So comparing B constant with hyperbolic function, so we have B constant here. So we try to compare with the previous analysis containing the hyperbolic function B. So which this Z prime over here. Okay, here Z prime only for B constant. So finally Z prime, this is equal to Z hyperbolic sines omega L over omega L. Okay. So to obtain the Y prime over 2, compare the A constant. So we try to compare again. This is A. So this is from the nominal 5. model with the hyperbolic function model. So we try to make a comparison and try to solve to make it more simple. And finally, after few arrangement, and we get the equivalent phi model for long line or long length line is represented by this diagram. Okay, so we still have the VS, IS. So this is a new Z or Z prime over here for long line. Okay, so we still have IL, IR. So this is Y prime over 2. So this is Y prime over 2. Okay, we have the capacitance. The shunt capacitance over here, which is the conductance value. So this is equal to Y hyperbolic tangent omega L over 2. Okay, over omega L over 2. Okay, so this is actually from this derivation. Okay, so this is Y prime over 2. All right. So to have a better understanding, so we go to example 7.5. So the distance is given by 250 kilometers. So this is 500 kV transmission line has per phase of Z as well as the YJ0 4.0 microsiemens per kilometer, Z 0.045 plus J 0.4 ohm per kilometer. So we have to find out the value of A, B, C, D, the parameter of the phi nominal phi model, so of the long transmission line. Okay, solution. So this is the characteristic impedance ZC. So the first equation we derived earlier. So Z value, again from here the Z and this is the Y. Just substitute into this equation, giving us the value of ZC T16.7 minus J 70.76. This is ohm. So we have the gamma. So this is actually equal to square root ZY. So this is just substitute again the value of Z and the value of Y. Okay, so this is the value of gamma. So we have Z prime, which is ZC, the characteristic Z over here into here, and then we have a hyperbolic sine YL. So this is, gamma here. This value, okay, just multiply by the L. L is 220. That means you need to multiply by this, multiply by 250. Okay, so this multiply by 250, so giving the sine omega L. So hyperbolic sines, and then multiply by again this ZC, multiply by this value, and giving the Z prime equal to 10.88 plus J 19.8.36. So what about the Y prime? So this is 1 over ZC. So this from again here, use it here. So we have a hyperbolic tangent. So we have omega L over 2. So again, this is omega. So multiply by 250. Okay, and don't forget to divide by 2. So hyperbolic tangent of this value, and then divided by ZC, multiplied by 2, giving the value of Y prime J 0.001. And we have done with the Z prime, so we have done with the Y prime, so we have done with the ZC and all that. So this is much easier in order to figure out the value of A, B, C, D parameter, where A equal to D equal to 1 plus Z prime, Y prime over 2. So again, this is just substitute the value of Z prime, Y prime, giving us the value of A and D as well. And then B equal to Z prime, this is straight away taken from the previous slide. So C equal to Y prime, okay, 1 plus Z prime, Y prime over 4. So giving value of C or parameter of C equal to J 0.0009. Alright, thank you very much again for your time and for your view. So we have completed with chapter number 7. Hopefully you will enjoy the video session. Thank you very much.